Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the exam for February-March 2023 in paper 4 for Physics IGCSE. The first question says that there is a boat crossing a river. The boat points at right angles to the riverbank and it travels at a speed of 3.5 meters per second relative to the water. So these are the riverbanks and the water is moving this way, but the boat, for example, is moving that way. It says perpendicular. It does not specify which direction, but we know that the direction of the travel of the water is perpendicular to the direction of the travel of the boat. So the boat is moving at a speed of 3.5 meters per second in this direction, and the river current acts at right angles to the direction of the boat. River current has a speed of 2.5 meters per second. So we have two velocities perpendicular to each other. By drawing a scale diagram or a vector diagram or by calculation, determine the speed and direction of the boat relative to the riverbank. Since most of you do not know how to calculate or create components for vectors, we will use a vector diagram, which is either using a head-to-tail method or a parallelogram method. Usually the head-to-tail method is much faster, but first we need to give a scale and know how the diagram will go. So we have, for example, an arrow to the right, which represents the direction of the velocity of the river or the current of the water, and we have an arrow to the north or upward vector. But these values 2.5 and 3.5 are too small to draw and get an accurate value while measuring using a ruler. So we will just magnify the values. We can multiply these by 2. When we get 3.5 times 2, you get 7 centimeters, and 2.5 times 2, you get 5 centimeters. That's actually a good scale for drawing this. So we basically multiplied by 2, which makes the scale of our drawing 1 centimeter, representing 0.5 meters per second. So every centimeter on our diagram will represent 0.5 meters per second. And we need to draw two vectors, one pointing to the right and one pointing upwards, or another person may use an arrow to the left and an arrow downwards. Either way, they should be perpendicular because it says so in the question. Okay, so we need to draw one arrow and then the other at the end of the arrow. That's how we use a head-to-tail method. So we will have to measure 90 degrees from the end of the first arrow to draw the second arrow. We can use the first one to be the current of the river, which is 2.5, and then draw the 3.5 meter per second. These are just the labels, but we will actually be drawing 5 centimeters and 7 centimeters. So now I will use a ruler to draw a 7 centimeter long arrow upward and a 5 centimeter long arrow to the right. So since the diagram will be going to the right and upwards, I will start from the left and down to leave for myself enough space to draw. First we draw the 5 centimeter arrow. Then we use a protractor to measure the angle from the end of that arrow and mark where it is pointing at 90 degrees. Now we remove the protractor and rotate the ruler so we can draw the 7 centimeter long line. There we go, 7 centimeters. After that we need to label and draw the arrows. So this is the 2.5 meters per second velocity, and this is the 3.5 meter per second velocity, and the resultant will be from the starting of the drawing to the ending of the drawing. So we put the ruler here, the 0 mark at the start of the first arrow. We tilt until we get to the end of the second arrow. Now this represents the resultant velocity, and now we label it resultant. To get the actual value of the speed, we need to measure the length of the resultant. In this case, in my drawing, it is 8.6 centimeters, but 8.6 centimeters is not a speed. We have a scale of 1 centimeter representing 0.5 meter per second, and we measured 8.6 centimeters. So we need to know what does this represent in meters per second. So we multiply by 0.5, which gives us 4.3 meters per second. And now for the direction. Whenever you're asked about the direction of a resultant vector quantity, a resultant velocity, or resultant force, you use a protractor to measure the angle from a direction which is already known or a direction which you are required to take as a reference. For example, in this question, it is required to measure the angle relative to the river bank. If you remember, we said the river banks were horizontal and this was the direction of the current. So the direction of the current, which is the 2.5 meter per second, is the direction of the river bank. So we will be measuring the angle between the resultant and the 2.5 meter per second velocity, which in this case is about 54 degrees. It's between 54 and 55, but nearer to the 54 degrees. So the answer will be 54 degrees. Question B says, speed is a scalar quantity and velocity is a vector quantity. State the names of one other scalar quantity and one other vector quantity. There are many quantities you should know in the syllabus. For example, scalar quantities, you have mass, time, volume, density, distance, energy, power. All these are scalar quantities. For vector quantities, we have forces, displacement, acceleration, moments, momentum, or electric current. Question 2 says, figure 2.1 shows a ship loaded with containers. The ship is made of steel. The density of steel is 7,800 kilogram per meter cubed, and the density of water is 1,000 kilogram per meter cubed, which is less. Explain why the ship floats in water. Normally, something with greater density than water would sink in water, but the ship is made of steel, which is more dense than water, and yet the ship floats. That's why it should be or appear confusing in this question. But it is not the density of the material of the ship or the object in the liquid. It is the total density of the whole object, which includes everything on the ship and including the air inside the ship. So the first thing we need to mention that floating depends on the total density of the object. The total density of the ship and its contents is less than the density of water. Right. Question B says the containers with the greatest mass are loaded near the bottom of the ship. State and explain the effect on the stability of the ship of loading the containers in this way. The heavier ones at the bottom and the lighter ones at the top. This will cause the center of gravity or the center of mass of the ship to be lower, which makes it more stable. So that's what we're going to write. The center of gravity of the ship will be low, which increases stability. Question C says a crane lifts a container 48 meters vertically upwards at height. The mass of the container is 30,000 kilograms. Calculate the energy transferred to the gravitational potential energy stored in the container. So the rule is the change in gravitational potential energy equals mg delta h. M is 30,000, G is 9.8, you should memorize that, and H is 48 meters. Always check that the mass is in kilograms and the height is in meters. This gives us 14,112,000 joules, but the numbers in the question are either two significant figures or one significant figure, so we should use one significant figure or one more significant. So we should stop here, which is approximately 14 million or 1.4 times 10 to the power of 7 joules. Next question says, state the principle of conservation of energy. This states that energy cannot be created nor destroyed. It can only transform or change form. Question B says a wind turbine has a maximum output power of 1.8 megawatts. The turbine operates at maximum power for 4 hours. Define the unit kilowatt hour. This is separated into two parts, kilowatt, which is power, and hour is time. So first, power multiplied by time gives us energy. So it is a unit of energy equal to power in kilowatt, between brackets 1000 watt, multiplied by time in hours. And you can also write the equation work equal power multiplied by time, or energy equals power multiplied by time. Question B double I says calculate the energy produced by the wind turbine operating at maximum power for 4 hours. So we have power and we have time and we multiply them, but it requires the answer in kilowatt hours, and we have the power in megawatts. To convert from megawatts to kilowatts, we have 10 to the power of 6, and we want to go to 10 to the power of 3. So that's times 10 to the power of 6 minus 3, which is 10 to the power of 3. So you take the 1.8 and make it times 10 to the power of 3 to convert from megawatt to kilowatt, then multiplied by the time in hours already. You don't need to change it because it is required as it is in the question, so multiplied by 4. This gives a value of 7,200 kilowatt hours. Question C says radiation from the sun is the main source of energy for most of our energy resources. State 2 energy resources that do not originate from the sun. These are two sources of energy anyway, which are geothermal, which is the heat from the inner core of the planet, and nuclear energy, which is from the energy stored in the nuclei of unstable elements. Question 4 says figure 4.1 shows a metal pan on an electric hot plate. The pan contains 200 centimeter cubed of water. That's volume, as a given. The pan is heated. The temperature of the water in the pan increases. Thermal energy is transferred through the metal pan by conduction. State and explain 2 ways that thermal energy is conducted in a metal. First, in general, conduction is the bombardment or collisions between neighboring molecules and transferring some of the kinetic energy. And in metals, there are also free electrons that travel between atoms or between molecules and share energy. So that's what we're going to write. Molecules with greater kinetic energy collide with adjacent or neighboring molecules and transfer some of their kinetic energy. Also, metals have free electrons which travel between molecules and transfer energy. Right. Question BI says the water boils and leaves a liquid as a gas. Explain in terms of forces and distances between particles why the gas occupies a much greater volume than it does as a liquid. First, you're required to mention forces and spaces between molecules. So in a gas, forces are much weaker, which allows molecules to move further apart, and the spaces between molecules are much greater than in liquids. That's why a gas occupies a greater volume. Okay, state 2 ways in which boiling differs from evaporation. First, evaporation takes place at the surface, boiling through the whole liquid. Another is that evaporation takes place at any temperature, boiling at certain temperature, which is called the boiling point. Let's see the next question. Question C says that water is replaced with 200 centimeter cubed of milk. The initial temperature of the milk is 20 degrees Celsius. The boiling point of milk is 95 degrees Celsius. The milk starts to boil when 60,700 joules of thermal energy has been transferred to it. The density of the milk is 1.03 grams per centimeter cubed. Calculate the specific heat capacity of the milk. We should be able to use the equation Q equals mc delta theta or delta T. Q is the energy, which is 60,700 joules. M is the mass of the milk, but we do not have mass. We have volume and we have density, but we already know that density equals mass over volume, so mass should be equal density multiplied by volume. So we will replace mass with density by volume, which is 1.03 times 200, and the volume is in centimeter cubed, same as this density, and we would use the unit for mass as grams. Then we multiply by C and multiply by delta theta, which is 95 minus 20. So we place C as a subject of formula, 60,700 joules over 1.03 multiplied by 200 multiplied by 95 minus 20, it is 75. This gives 3.9288026, but we will not be using that many significant figures. 1.03 is 3 significant. This could be 1 or 2 or 3. This is 2. This is 3. So we can use 3 significant figures to be safe. And the 8 rounds up the 2. So we will write 3.93 joules per gram degrees Celsius, since we used mass as in grams. Another person could use the mass in kilograms, and the number will be 1000 times greater, but the unit will be joule per kilogram degrees Celsius. In question 5, question A says, figure 5.1 shows a semicircular transparent plastic block. A ray of light is incident normally on the curved surface of the block. The refractive index of the plastic is 1.5. So this is 90 degrees. So at this point there will be change in speed, but there will be no change in direction, since the ray is normal to the surface or the boundary between two media, or is on the normal line. First, we are required to calculate the critical angle, and we have a rule for that. The refractive index equals 1 over sine the critical angle. So sine the critical angle is equal to 1 over n, which is 1 over 1.5. Then we do an inverse sine on the calculator. We use shift sine answer. First we divide 1 by 1.5, and shift sine answer gives an approximate value of 42 degrees. It is actually 41.8103, but we will approximate it to 2 significant figures. Question I says, on figure 5.1, draw the path of the ray in the block and after the ray emerges from the block. So we will use a protractor just to check whether the angle of incidence inside the block is greater than or smaller than the critical angle. First we need to continue the line until it reaches the boundary between the glass and the air, and then measure the angle. The angle from the 90 degrees from the normal is 60 degrees, which is much greater than 42, so there will be total internal reflection. Since the angle of incidence is greater than the critical angle, there will be total internal reflection inside the block with the same angle. So we need to mark the 60 degrees here. From the normal we measure 60 degrees, and we mark the point where we will connect the ray. Then we draw a straight line towards the 60 degrees. At this point, since the ray is incident normal to the surface from the beginning, it will reach the center of the block. So leaving the block, it will also hit the surface at 90 degrees, so the ray of light will not bend going out either. And we check if we are required to label this ray or not. We are not required to label it, so this is the shape of the ray. And just to say that we are measuring angles, we will use a protractor to draw a perpendicular line at the center of the block as a normal line. But since the normal line is not a real ray or an actual line, we will just draw it as a dashed line or a dotted line. So the angle of incidence on the left is equal to the angle of reflection on the right. The next question is about lenses. Question B says, figure 5.2 is a full-scale diagram of a lens and an object O. The point marked F shows the position of the principal focus of the lens. Determine the focal length of the lens. So using a ruler, we place it here, and we have 1, 2, 3, 4, 5, 6, 7.3, approximately 7.3 centimeters. Yours may be different since I'm using a soft copy of the document. Next, it says, on figure 5.2, draw 2 rays from the object to locate the image, label the image I. First, we have 3 types of rays. One which is parallel to the principal axis, the horizontal long line is the principal axis, and then it goes to the focal point on the other side. The other one, the next one, is one that passes through the optical center, which is the center of the lens, and just continues straight. The other one should be from the focal point or toward the focal point, but this will not be useful in this case because the object is between the focus and the lens, which gives us a virtual image. So we will use the first two lines. You can measure the length of this arrow and measure it again on the center of the lens, just to make sure that you are drawing a line that is parallel to the principal axis. This is the first ray. But in order to draw the continuation of this ray, we need to find the focal point. So again, we place the rule here and measure the same distance from the center of the lens. So this is where the other focus of the lens exists. Now we can draw the line, but we will give it an extension backwards. Since the image will be in this area. Also we will draw another ray which comes from the top of the object towards the center of the lens and continues straight, no bending. And we will also be extending that line backwards. Then we can remove parts of the extensions to show that these are not the real rays of light, and we mark this point as the image, and we draw the image as an arrow towards the principal axis, and it will be pointing upwards. Always when you create a virtual image using a convex lens, it creates an upright enlarged image, and you will always have to extend the rays backwards so you can get an intersection to form the image. And since it was required to label it I, we labeled it I. If the object was behind the focal point, you will expect the image to be at this part and there will be no extensions. The rays will intersect on their own. Question C says figure 4.3 shows a simplified diagram of an eye with rays from a distant object and the path of the rays inside the eye of a person with short sight. On figure 5.4, which is the one down there, draw an additional lens outside the eye to correct short-sightedness and show the path of the rays inside the eye. So here the problem is the light should intersect at the base of the eye, but intersects a little earlier. So we need the rays of light to diverge a little bit so they can reach the base of the eye. So we will be using a diverging lens or the concave lens. First we draw the principal axis of the lens and the central line, which is perpendicular. And you don't need to be an artist to draw the next part. So you just draw a concave lens like that. And here the rays entered near to each other. You need to make them further apart so they can converge then towards the base of the eye. So the rays diverged at first, and they were coming parallel to the axis before the concave lens, and then from the inner lens of the eye they will converge towards the base of the eye. So we connect this line to the base and the other line to the same point. So this is how it is corrected. First you diverge the beams, then it converges parallel to the original direction, so technically using the same lens inside the eye, but diverging the beams before the eye. Question 6a says sound waves have compression and rarefaction. Explain what is meant by compression and rarefaction. Compression is a region where molecules are close to each other and have high pressure. A rarefaction is a region where the molecules are far apart and have low pressure. Right. Question B says we can see light from the sun, but we cannot hear any sound from it. State the reason for this. This is because sound cannot travel through vacuum. which has or contains no molecules, which means no molecules to form compressions or rarefactions. Question C says, during a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of the thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is heard 9 seconds after the lightning is seen. The speed of sound in air is 340 meters per second, so we have time and we have speed, and we are required to calculate the distance from the thunderstorm. Assuming that light does not take any time to reach the observer, we will base our calculations that the time 9 seconds is actually the time that the sound takes, not the time between seeing and hearing. So we will use speed equal distance over time, since waves travel at constant speed in the same medium. This gives us that distance equals speed multiplied by time, which is 340 multiplied by 9. This is 3060 meters. We could approximate this to 3000 meters as two significant figures, but we are allowed one more significant figure, so we can just write it as it is in this case. Question D says, in a lightning strike, there is a current of 3.0 times 10 to the power 4 amperes, that's I, for 48 milliseconds, that's time. Calculate the charge that flows. We can calculate the charge by multiplied current and time. 3 times 10 to the power 4 multiplied by 48 times 10 to the power of negative 3 to convert from milliseconds into seconds. This gives a charge of 1440 coulombs. Okay, now we go to the next question. Question 7a says, define potential difference, which is the energy or the work done or needed to move a unit charge, which is 1 coulomb, between 2 points. If it said define electromotive force, instead of using between 2 points, we say across a complete circuit. State the equation which defines electromotive force. EMF equals work over charge, or we can rewrite it as E equals W over Q. We usually use the symbol V for potential difference or EMF, but here you are required to use E. BII says the EMF of a battery is 9 volts and the battery is in a circuit. Calculate the work done by the battery, which is the energy, when it moves a charge of 30 coulombs around a complete circuit. So we have E, which is the voltage, 9 volts, and we have Q, which is 30 coulombs, and we need work. Work equals potential difference or EMF multiplied by charge, by rearranging the equation in I. So we multiply 9.0 times 30, which gives 270 joules. Now question C says a circuit consists of a DC power supply, direct current power supply, a lamp, and a thermistor. Draw a circuit diagram of these components connected in series. So a direct current power supply, it can be represented using a battery, which is a cell connected to another cell at least, or a number of cells. And then we connect a thermistor, which is basically a resistor, a rectangle, and like a spatula drawn across it, and a lamp, which is a circle with a large X inside of it, and we close the circuit. The DC power supply can also be represented using two circles and labeling one of them positive and the other negative. You don't need to do that for the battery symbol, since the longer line means positive, the shorter lines mean negative. Question CII says explain what happens in the circuit you have drawn in CI when the temperature of the thermistor increases. First, we need to mention that as temperature increases, the resistance of the thermistor decreases and the total resistance of the circuit decreases, increasing the current. And since there was a lamp, we need to say and the brightness of the lamp. Question 8 says figure 8.1 shows a horizontal flat coil in a magnetic field. The coil is connected to a cell. The coil rotates. Determine the direction of movement of the side AB relative to the plane of the coil. First, we need to identify the direction of the current and the magnetic field. The magnetic field, we can say that it is pointing from north to south to the right. So the right-left direction is already reserved. We cannot say that the wire will either move right or left. And the current will go out of the positive terminal, moving into the wire AB from A to B. When you have an arrow that is pointing inclined but upward, that's a current into the page. So we have a current into the page, so also into and out of the page are reserved. So the wire will either be said to be moving upwards or downwards. But which direction? We will be using Fleming's left hand rule. So by placing our fingers in this orientation, we can say that we have the magnetic field pointing to the right and the middle finger representing current into the page. The thumb is actually pointing down. So wire AB will move downwards. Now explain how you determine the direction in A. We will say using Fleming's left hand rule, where magnetic field is pointing to the right and current into the page. Question C says, state and explain what happens to the coil as it reaches the vertical position. So now the coil was like this. This is side AB, was going downwards. The other side will be moving upwards, so it rotates counterclockwise. Eventually the coil will be in this position, and wire AB went down, the other wire went up. At this point the forces are on the same line, so there will be no more moment, but it keeps rotating due to its inertia. So we will say there will be no more moment or torque, but the coil keeps rotating due to inertia or momentum. But after that, the forces will make the wire rotate in the opposite direction. So we write then the coil swings backwards. So the coil will just move on to this direction, then rotate in the opposite direction, then rotate in the opposite direction, and keep swinging until it stops. So we write until it stops. Question D says, to operate as a motor, a split ring commutator and brushes are added to the ports shown in figure 8.1 to solve the problem of the swinging and then stopping coil. Explain the effects of the split ring commutator and the brushes on the action of the motor. First, we need to say the function of the split ring commutator, which is that it reverses the current and the forces in the coil every half cycle, so that the coil keeps rotating in the same direction and does not just rock forward and backward until it stops. Now we go to the next question. Question 9a says, a nuclear power station has a reactor where controlled nuclear fission of uranium-235 takes place. Explain what is meant by nuclear fission. And we have 3 marks to fill. First, we say that a heavy, unstable nucleus splits into 2 lighter, more stable nuclei and releases energy. And we must say that this energy is due to loss in mass. So during this reaction, the total mass of the particles decreases, and this mass changes into energy. Usually the type of energy, if you are asked, is either kinetic energy or gamma radiation, or both. In this case of nuclear fission, it's usually both gamma radiation and kinetic energy, which heats up the reactor, and we use this heat then to vaporize water and convert this energy into electric energy. Question II says, state one advantage and one disadvantage of generating electrical power in nuclear power stations compared with electrical power generated using wind turbines. First of all, the advantage is it is reliable or controllable, has higher output. The disadvantage is for nuclear power station is the risk of contamination or irradiation. Contamination usually happens due to explosions, due to overheating of the reactor, and irradiation is basically the radiation leaking outside the nuclear power station. Question B says, deuterium is an isotope of hydrogen with 1 proton and 1 neutron. Nuclear fusion occurs when 2 nuclei of deuterium combine. An isotope of helium and a neutron are formed after the fusion. Use nuclide notation to write down the nuclide equation for this reaction. First, The question gave us the symbol for hydrogen, and we have 2 hydrogen nuclides, 1 proton, which gives proton number 1, and 1 neutron. 1 proton and 1 neutron gives a nucleon number of 2. This gives us helium, and we have the helium symbol. And we should remember that the symbol for a neutron is a small letter n with 0 at the bottom and 1 on the top. And now we balance the numbers. So we have on the left side 2 and 2 gives us 4. So the top numbers should also add to 4 on the right side. So we have here 3. And at the bottom we have on the left side of the equation 2. 1 and 1 it's 2. So there should be 2 here also. You might be deceived in this type of question because you know that helium nucleus for an alpha particle, it should be 4 and 2, but it did not say helium nucleus as an alpha particle. It said an isotope of helium, which could have a different number of neutrons, so different number of nucleons. So that's why the question gave 3 instead of 4. This is another isotope of helium. The last question in this exam was question 10. Question 10a says the time taken for Mars to orbit the Sun is 690 Earth days. The average orbit radius of Mars is 2.28 times 10 to the power of 8 kilometers. An Earth day is 24 hours, and we are required to calculate the orbital speed of Mars in kilometers per second. So we need to convert the days into seconds. First, the orbit is usually considered a circular orbit, so we will use distance as the circumference of a circle, which is 2 pi r, and then divide by time, which is the periodic time of rotation. Here we have 2 pi multiplied by 2.28 times 10 to the power of 8, and we will leave it in kilometers as it is, since we are not required to convert anything. The unit is needed in kilometers. Then we divide that by the periodic time of oscillation or rotation of the planet, which is 690 days. So we multiply that by 24 hours, then 60 minutes, then 60 seconds. This gives 17.27149 approximately. The values here are all either 2 significant or 3 significant. We can use 3 significant. 17.2 kilometers per second. Question B says, state the shape of the orbits of the planets. We are supposed to know that they are elliptical in shape or oval in shape. Question C says, light from a distant galaxy is redshifted. Explain what is meant by a redshift. It is the apparent increase in wavelength, or we can say decrease in frequency due to the source of the light moving away from the observer. Double I state the quantity that the redshift of the galaxy is used to calculate. We use this to calculate the relative speed between the galaxy and the Earth. This was the end of the exam of February-March 2023. I wish you all good luck in the exams, and I will see you in another video.